Have you ever really stopped to think about what happens when you type go build? I mean, we write this clean, readable Go code, and then, poof, it somehow becomes this stream of ones and zeros that your CPU just magically understands. Well, today, we're going to pull back that curtain. We're going to trace the exact journey your code takes from a simple function all the way down to the executable machine code.
Take a look at this. It's about as simple as it gets, right? An add function. But honestly, most of us, if we're being truthful, see the process of how this becomes something the CPU can run as a total black box. But here's the thing. Understanding that process is the secret to writing seriously high-performance Go. Because every single line you write, every decision you make, has a direct, tangible consequence on the final machine code.
So, here's our game plan. We're going to follow your code through the final stages of the compiler's pipeline. We'll see how it gets customized for specific hardware, how it's optimized for pure speed, and finally, how it's all forged into the machine code that actually runs on your computer. Let's dive in.
Okay, so we're jumping in partway through the compilation process. By now, your Go code has already been parsed, type-checked, and transformed into a really special format called static single assignment, or SSA. You can think of SSA as a super optimized, abstract blueprint of your code. Its one golden rule is that every variable is assigned a value exactly once. This makes it incredibly easy for the compiler to analyze and optimize, but it's still generic. It can't run on any real hardware just yet.
Now, at this point, the compiler has already done a ton of heavy lifting. It's figured out what your functions do, it's probably eliminated some redundant safety checks, and most importantly, it's performed a critical step called escape analysis. This is where the compiler gets to be a detective. It analyzes the lifetime of every single variable to decide where it should live, on the lightning-fast stack, which is for short-lived data, or on the slower, more globally accessible heap for data that needs to stick around. This one decision has absolutely massive performance implications, as we're about to see.
And that is the central question, isn't it? This whole phase of compilation is designed to solve this one problem. We have this perfect logical blueprint in SSA form, but it's totally generic. It doesn't speak Intel x86, and it doesn't speak Apple M-series ARM. Each processor has its own unique language, its own instruction set, its own rules of engagement. The real challenge is translating our universal blueprint into something that a physical piece of silicon can actually understand.
So, let's get into the first step of that translation. It's a stage called ABI lowering. I want you to think of our SSA code as a master blueprint for a house. Well, ABI lowering is like taking that blueprint to the local city office to get it stamped. You have to adapt the plan to the local building codes, the specific, unchangeable rules of the hardware you're building for. You can't just build whatever you want, you have to follow the rules. Same thing with code.
And that set of rules is called the Application Binary Interface, or ABI. You can think of it as the official contract. It's the rulebook that dictates how different pieces of software talk to each other at the absolute lowest level. It defines how functions call each other, how they pass data back and forth. It's the fundamental grammar of machine-level communication. It's what makes the whole system work together without falling apart.
And every CPU architecture has its own unique ABI. An ARM64 chip plays by different rules than an ARM64 chip. The ABI gets into the nitty-gritty. It says, okay, to call a function, should you put the arguments in fast CPU registers or push them onto the slower memory stack? It defines exactly where a function's return value has to be placed so the caller can find it. It's incredibly detailed, and it's absolutely critical for making sure the program is stable. And this slide just illustrates the transformation perfectly. On the left, you've got the abstract, machine-independent idea from our SSA blueprint, hey, call this function with two values. But on the right, you see the concrete, ABI-aware reality for a typical 64-bit system. That abstract idea gets lowered into a specific sequence. First, put the first value in the RDI register, then put the second value in the RSI register, and only then can you execute the hardware's call instruction. The logic is the same, but now it's speaking the native language of the CPU.
And believe me, this isn't just some academic detail. It has a huge impact on performance. Before Go 1.17, the compiler actually passed all function arguments on the stack. Now that was simpler, but it was also kind of slow because it always meant going out to memory. The Go team completely redesigned the ABI to use registers for popular architectures, just like in our example. And that one change, deep inside the compiler, gave almost every Go program on the planet a free 5 to 10% performance boost, without developers having to change a single line of code. Pretty cool, huh?
Okay, so our code is now correct. It follows all the hardware rules. But is it fast? Well, that's what this next stage is all about. Register allocation. This is one of the most critical make-or-break parts of any modern compiler. It's all about planning the most efficient way to do calculations by deciding which pieces of data get to live in the CPU's super-fast registers at any given moment.
And you just have to look at this chart to see why this is so important. The difference in speed is just staggering. A CPU can only do math on data that's physically inside its registers. Getting data from those registers is basically instant. We're talking 1 nanosecond. But if that data is on the stack, it has to be fetched from memory first, which is tens or even hundreds of times slower. And the heap? Oh man, that can be 1,000 times slower. The whole game of register allocation is to avoid those slow memory trips as much as humanly possible.
Here's an analogy I like. Imagine you're cooking in a kitchen. The registers are your hands. You can only work with what's literally in your hands right now, but it's instant. The stack is like a bag of ingredients on the counter right next to you. It's got everything for the current recipe, and it's pretty quick to grab from. But the heap is the big storage room down the hall. It has all your supplies, sure, but you have to stop everything you're doing, walk all the way over there, and find what you need. It's slow, and it breaks your flow. A good compiler, just like a good chef, plans ahead to keep the most important ingredients in its hands at all times.
So here's the crucial point to remember. Register allocation is the plan that the compiler makes at compile time. It's the blueprint for what the CPU is going to do at runtime. Escape analysis already decided if a variable's home is the stack or the heap. Now, register allocation looks at a line like y is equal to x plus 5 and says, okay, at runtime, the CPU must first load the value of x from the stack into a register, then do the addition inside that register, and finally store the result from the register back into y's spot on the stack. Minimizing those loads and stores is the name of the game.
All right, this is it. This is the moment we've been building towards. We've followed the hardware rules, we've made an optimal plan for speed, and now we finally convert all of these high-level decisions into the actual nuts and bolts, the final sequence of binary machine instructions that the processor will execute directly.
And you can literally see the consequences of that early escape analysis decision right here in the generated code. It's plain as day. A variable on the stack translates to simple, direct, and incredibly fast machine instructions. Look at that. Sub SP #16 just moves the stack pointer to make some space. It's one instruction. It's beautiful. But a variable that escaped to the heap, that's a whole different story. That requires a call to a complex function deep in the Go runtime, like runtime.newObject. This is so much more expensive. Seeing call runtime.mst in your compiled code is a dead giveaway that a heap allocation is happening. Understanding this distinction is absolutely fundamental to writing high-performance Go. And if you're into this stuff, you should subscribe to our GoSyn channel for deep dives into Golang internals, architecture, and execution flow. Advanced concepts rarely covered on YouTube, and it's all available for free.
So, as the compiler is generating all this code, it's also doing some critical bookkeeping for its good friend, the Go runtime, specifically for the garbage collector. It creates these things called stack maps. You can think of a stack map as a treasure map that the compiler leaves for the GC. For any point in your code where the GC might need to run, this map tells it exactly which spots on a function stack hold pointers to the heap and which ones are just simple values like integers.
And this precision is a really big deal. Because of these stack maps, Go's garbage collector is what we call precise. It knows with 100% certainty what is and what is not a pointer. This is so much better than a conservative GC, which basically has to guess by looking for numbers that look like memory addresses. That guesswork is slow, and it can lead to some really nasty bugs or memory leaks if it misinterprets a random integer as a valid pointer. Precision is just faster and way, way safer.
So at this point, we've basically manufactured all the individual parts of our program, the machine code for every function in every file. But it's not a finished product yet. It's more like a flat pack from IKEA. Each package is compiled into an intermediate component called an object file. Think of it as a prefabricated module, all ready for final assembly.
So this object file, it usually has a .o extension. It contains the raw machine code we just generated, plus all that handy GC metadata. But here's the key. The memory addresses aren't final yet. Instead of calling a function at, say, address 0x401000, the code uses a placeholder, a symbolic name like main.add or fmt.println. The object file also contains a list called relocation records. That's basically a to-do list for the next phase, noting every single place a placeholder was used.
And this brings us to the final assembler, the linker. The linker is the master architect. It takes all of these individual object files, one for your main package, one for the FMT package you imported, plus all the object files for the Go runtime itself, and it stitches them all together into one coherent program. It figures out the final memory layout, and then it goes through that to-do list, replacing every single one of those symbolic placeholders with the final concrete memory address.
Okay, let's put this all together now. We're going to trace one final example through the entire process, from start to finish. You'll see how every single decision we talked about, escape analysis, register allocation, linking, has a tangible, visible impact on the final code.
We're going to use this add function here. Now, I've written this one specifically to use all three main memory types. It has a local variable x that's destined for the stack. It creates a slice, and we know its backing data is going to be allocated on the heap. It calculates a result, and that's going to happen in registers. And it even touches a global count variable, which lives in a special data section of the final program. This table right here, this perfectly summarizes our entire journey. Just look at each row. The local variable x, it becomes direct stack operations right away, and the linker doesn't even need to touch it. The heap allocated slice, it starts as a call to a symbol, runtime.makeslice, which the linker then patches up with a final address, like 0x45,000. The result of our calculation, it just lives briefly in registers, all according to the compiler's plan. And that global count, it starts as a symbolic reference, which the linker finally pins to a specific memory address, 0x5000. Every type of variable has its own unique path, and it's all sealed in the final machine code.
So the next time you write a line of Go, I want you to remember the incredible journey it's about to take. It's not magic. It's a brilliant multi-stage process of refinement, from an abstract idea to a set of rules for your hardware to a carefully orchestrated dance of data between registers, the stack, and the heap. A simple make ent 5 isn't just a line of code anymore, is it? It's a decision. It's a request that results in a call to the runtime, a heap allocation, and future work for the garbage collector. Understanding this flow from your brain to machine code is what empowers you to write truly better, more efficient programs.